Now, although this course deals primarily with non-relativistic mechanics, I would like to give at least an outlook on special relativity. We had talked about space and time and basically the arena in which mechanics unfolds, and we had so far considered non-relativistic space and time. And I would like you to recall this picture here, where we had looked at the motion of a mechanical body relative to two different reference frames. This was a so-called space-time diagram, where the vertical axis is time, and in the horizontal planes you have space. Obviously, I have to suppress one space dimension in order to be able to draw it. So each of these horizontal slices represents ordinary space, and upwards you have time. So look on the left-hand side. There you have observer number 1. Observer number 1 is not moving. That's an inertial frame, and the position in space doesn't change, but observer number 1 is just moving along a vertical line. So time is running, the clock is ticking, the observer moves upwards, but it doesn't move horizontally. It's an observer at rest. And indicated, you see in the blue vectors that span the horizontal plane. These are the basis vectors in ordinary space. Here it's just E1 and E2. And then you have, associated with each horizontal plane, you have a clock reading. So I symbolize that with this little clock next to the reference frame, and you see below it's time 0, and then you move upwards and the clock is ticking. Then you have another observer. That's the second green line. This is sort of a diagonal line, meaning that the second observer is moving. It's not at rest anymore. It's also going upwards because time is ticking, but it's also going, at the same time, it's going sideways. So the observer is moving in ordinary space. And the slope of that line is obviously related to the velocity of the second observer. And then in the middle, you have the black line, this curved line. That's the world line. One talks about the world line here of an arbitrary mechanical body. So it performs an arbitrary motion. Also, its clock is ticking, so it's moving upwards, and it's moving in space. So it's wiggling back and forth, let's say, and that's the motion of some body. And now the two observers, which move along the green lines, they look at this body that moves along the black line, and they describe the motion of the body in their respective frame. Now each point along the line, along the black line, constitutes an event. The event is the body is here. That's an event. So you see the black dot up there. That's an event. It says the body is here. And the first observer describes the position in space of the body by the vector x of t. That's this purple vector, the left purple vector, x of t. And then the first observer can assign components. So it simply represents x of t in its basis, e1 and e2, with components x1, x2. And this describes the position of the body in space. the observer also assigns a time to this event. The observer simply reads his or her own clock, and the clock says it's time t. Now the second observer, on the second green line, describes the spatial position of the body with the other purple vector, x prime. And this vector x prime has components x1 prime and x2 prime in the basis e1 prime and e2 prime of the second observer. Yeah, so the second observer will describe the spatial position, or the spatial location of that event by components x1 prime, x2 prime, and will assign to this event a time, and that's the reading of the clock of the second observer. And you see there the clock of the second observer shows time t prime, which is t minus s. And it's shifted with respect to the clock of the first observer. Now these space-time diagrams, where we have sort of the vertical direction is time and the horizontal direction or directions are ordinary space, they are very useful to describe relativity. Yeah? So what I would like to do is copy this diagram and then start to discuss what changes in a relativistic picture. So here we go. Here's the diagram from the discussion of non-relativistic reference frames. And I'd like to make a few modifications which have nothing to do with relativity yet, but it's some preparatory work to make the transition as natural as possible. So one modification I would like to make. Up to now we had basis vectors only for ordinary space. I would like to introduce an additional basis vector that points in the direction of time. So at this position here, for example, I would like to introduce an additional basis vector that now points in the direction of the time axis. And likewise down here. So we are, even though I can't draw all 4 dimensions, but in principle we are now in 4-dimensional space-time. And at each point in 4-dimensional space-time, there are 4 basis vectors. 3 basis vectors spanning ordinary space, and now a 4th basis vector pointing in the direction of time. I drew these vectors for the first observer. What about the second observer that moves with finite velocity? There, the time vector will point in that direction, will point in the direction of the world line of this observer. So that's E-t prime. Why is that? Because what's the meaning of this basis vector? Let's go back to the first observer where it's simpler. Let's start with one of the spatial basis vectors. When I move along basis vector E1, let's say, so within this horizontal plane, this means I vary the x component of space, I keep the other spatial components constant, and I also keep time constant. When I move along this new basis vector Et, this means that I leave all the spatial components invariant. I just change the time coordinate with respect to the reference frame of this particular observer. Now, for the second observer, keeping the spatial components constant means moving along the world line of that observer. Because look at the point where the basis vector et prime originates, that point has, with respect to the second observer, has all spatial components equal to 0. Okay? When you move along this red basis vector et prime, you go to the tip of that vector, to the end of that vector. At that point, for the second observer, the spatial components are still 0. Only the time component has changed. Yeah? So the vector et prime points in that direction where the spatial components don't vary for that particular observer, only the time varies. And this means moving along the world line, because at each point along the world line, the spatial components for that observer are 0, because there is always the origin of the spatial coordinate system at any given time. Yeah? So et prime, therefore, is tilted with respect to et. Next, let me eliminate the purple vectors, and I would also like to eliminate the distance vector d. I got rid of the purple vectors and of the distance vector d. So I eliminated the position vectors, the purple vectors, which were position vectors in ordinary space. And also the distance vector between the origins of the two reference frames was a distance vector in ordinary three-dimensional space. And instead, I would like to introduce vectors in space-time, four-dimensional vectors. I would like to denote with this red dot here the origin of the four-dimensional reference frame of the first observer, in the sense that it's the origin of the three-dimensional blue reference frame, but it's also the point where the clock of the observer shows 0. It's where the clock of the first observer starts to tick, right? That's the first red dot. And let me mark the same for the second observer. This is the event, this is the point in space-time where the clock of the second observer starts to run, where it shows time 0. And it's also, because it's on the world line of the second observer, it's also the origin of the reference frame of the reference frame in space. Now these two origins of the space-time reference frames, they are some distance vector apart, and this distance vector is now a four-dimensional vector. It's a vector in space-time. And I would like to denote that distance vector by S, and instead of an underline, which I reserve for three-dimensional vectors, I draw a curly underline, which means a four-dimensional vector. Or in short, a 4 vector. Yeah? So all vectors with the curly underline are 4 vectors in space-time. And now let's consider the event up there, the black dot. The event says, here's the body. This event, with respect to the first observer, has four-dimensional position vector, which goes from the origin, this origin, to that black point. And let me call that X with a curly underline. That's the four-dimensional vector characterizing that event with respect to the first observer. And with respect to the second observer, it's this 4 vector that's X curly underline primed. And of course these two vectors are related by this distance vector S, curly underline. Now we can write for example, the 4-vector X. We can expand that in the basis, the space-time basis of the first observer. We can write that as t times basis vector et plus sum over I going from 1 to 3 xi, that's the spatial component of the location of that event in ordinary space, times basis vector ei. Maybe to be consistent, I should now use, because these are all vectors in 4-dimensional space now, to be consistent, I should use everywhere the curly underlines. We said the first observer is at rest. It's just moving on the world line vertically. So this is an inertial frame. The second observer, so far we have not constrained in any way the motion of the second observer, so we cannot be sure yet that this is an inertial frame. We just call the frame of the second observer, we call that f prime. What we require in any case, however, is that f primed sees the same space-time structure as f. What does that entail? Does that give any conditions on the way that the basis vectors E primed of the observer F primed are related to the basis vectors of the observer F? We said non-relativistically, space-time structure has 3 features. First of all observers agree on simultaneity. Secondly, when we have 2 simultaneous events, then the spatial distance between these events is the same for all observers. And thirdly, the duration, when we have 2 events at different times, then the observers need not agree on the time itself, but they do agree on the duration, on the time that elapses between 2 events. So they observe the same time difference between 2 events. Let's start with the first 2 features, namely when we require that f prime sees the same space-time structure as f, then this means in particular that the transformation from f to f prime preserves simultaneity and spatial distance of simultaneous events. For the observer f, the spatial basis vectors, so E1, E2, E3, which span ordinary space, in this picture they span this horizontal plane. And you can say the plane spanned by E1, E2, E3, this horizontal plane, that's a subspace of space-time, and it's a subspace of simultaneous events. So all events that happen at the same time lie in this horizontal plane. When we say, when going from f to f primed, we preserve simultaneity, then it must be true that this horizontal plane is also spanned by E1 primed, E2 primed, and E3 primed. So E1 primed, E2 primed, E3 primed must lie in the same horizontal plane as E1, E2, E3. That's one consequence. Now, at the same time, we also preserve, for simultaneous events, we preserve spatial distance. This means that the basis vectors ei prime for I going from 1 to 3, so this, the spatial basis vectors only, not the new basis vector et that we had introduced, that they must be related to the original basis vectors in the frame F by an orthogonal transformation, by a rotation. This is one consequence of the requirement that we must preserve spatial structure. The other requirement was that f and f prime measure the same duration, the same time difference between two events. Now this implies the following. You can understand this basis vector et that points in the direction of time. Going along this basis vector, you can imagine that as one tick of your clock. So if the observer f goes from the beginning of this vector to the end of this red vector, then you can interpret that as one tick of your clock. So the length of that vector is basically your unit of time. Just as for the spatial basis vectors, they are unit vectors and they determine the units of your length scale. Now, if you go from one horizontal plane to the next, they differ by a certain time interval, and we said that both f and f prime must measure the same time interval. So this means that, say, the first horizontal plane is the one that I drew. That's where the start of these red vectors lies. And then you go to the next horizontal plane, that's one level up, and let's say that lies here at the tip of this red vector. That's where the next horizontal plane is. Well, this is one unit of time later, because it's just the length of that basis vector et. We require that observer f prime also measures that this horizontal plane is one unit later. So let me sketch a horizontal line here. The tips of both red vectors must lie in the same horizontal plane. That's what we mean by saying that we measure the same time interval by going from one horizontal plane to the next horizontal plane. What does that imply for the basis vector et prime? This implies for the basis vector et prime, well, if it lies in the same horizontal plane, it means it's composed of two motions, if you like. It's like going one level up with the basis vector et without a prime. That means going up to the next horizontal plane. And then it can differ only sort of by a vector that lies in this horizontal plane. And that's some linear combination of the spatial vectors. So the difference between et prime and et can only be some linear combination of spatial basis vectors. And the coefficients in front of the spatial basis vectors are just the velocity with which the observer f prime moves relative to the observer f. These are consequences of the requirement that f prime sees the same spacetime structure. If in addition we require that f prime is an inertial frame like f, this means that the two are related by a Galileo transformation. That's the definition of a Galileo transformation, that it relates inertial frames to inertial frames. What is an inertial frame? It's a frame in which an isolated body moves uniformly. So if F sees a uniform motion, then F prime must see a uniform motion too. This is guaranteed only if two requirements are satisfied. We learned that in the context of our discussion of the Galileo transformation. The motion of observer F prime must be uniform with respect to observer F. So the world line of observer F prime must be a straight line. And the second consequence is that this rotation in ordinary three-dimensional space that relates the spatial basis vectors, that rotation R that we had introduced above, that in general can be time dependent, but if you want F prime to be an inertial frame, then this must be constant. It may not depend on time. This R is constant. And now a transformation that satisfies both these groups of requirements, preserving space-time structure and also mapping inertial frame to inertial frame, such a transformation we call the Galileo transformation. Now let's go relativistic. Let me just quickly summarize what we learned about Galileo transformations. Let me start with the second class of requirements, namely that one maps uniform motion to uniform, and hence the world line of the observer prime is a straight line. And then the other group of requirements was that we preserve space-time structure, in particular simultaneity, spatial distance of simultaneous events, and the duration of time intervals. This is non-relativistic. Relativistically, you have the same concept. You also look at transformations from one reference frame to the other reference frame that map uniform motion to uniform motion and preserve space-time structure. Only that the space-time structure is different. Space-time structure is no longer characterized by these three features that are listed here, but space-time structure is characterized differently. And that's what we're going to consider next. Here I already want to introduce the name of these transformations in the relativistic case. These are called Lorentz transformations. And in the sort of most general case, there's a distinction between inhomogeneous and homogeneous Lorentz transformations. What I'm going to talk about for the time being are the more general kinds of transformations, which are inhomogeneous Lorentz transformations. And they satisfy the same requirement number one, that they map uniform motion to uniform motion. They also preserve space-time structure, but the features of space-time structure are different. Let's look at this more closely. What's the difference in space-time structure between non-relativistic and relativistic? And the key aspect to focus on is the causal structure in space-time. Let's consider the causal structure in non-relativistic spacetime versus the causal structure in relativistic spacetime. For simplicity, let me now suppress two of the three spatial dimensions. So rather than horizontal planes, I just have horizontal lines. So I'll just draw one spatial dimension, which I denote by x, and the time axis. And let us consider in space-time some event. Non-relativistically, time is an absolute property. We saw that different observers always measure the same length of time intervals. So up to an additive constant, time is absolute. And this implies that also past and future are simply defined by time. So this event happens at a certain time, and all events that happen at an earlier time in this green shaded area, these constitute the past of the event in question. So, and all the events that happen in this green shaded area are potential causes of the event. Right? So these are all potential causes of the event. Then all events that happen at a time later than t, so all events above the blue line in this red shaded area constitute the future of the event, and all events in the future in this red shaded area are potential effects of our event. Now, what happens relativistically? The key difference is that there's a speed limit for information transfer. So if we have here our event, then the potential causes of this event are not, as in the non-relativistic case, all events that had happened at a time earlier than the time of the event. But since effects can propagate only at a finite speed below this speed limit, the potential causes are limited to this cone that opens to the bottom. Yeah? So you have here a finite maximum speed of, say, information transfer or sort of propagation of causal effects. The same applies to the future. Here too, it's not the case that all events at a time larger than the time of this event are potential effects of the event, but sort of the information about this event and causal influence from this event can propagate only with a finite speed below this maximum speed, and hence the events that can be causally influenced by our event here lie in another cone that opens to the top. So here you have potential effects. Now, you all know, of course, that this speed limit, this maximum speed of information transfer, is the speed of light. For the purposes of discussion of relativity, you don't have to know that yet. the only relevant information is that there is some finite maximum speed, whatever it is. However, sort of course, inspired by the fact that it is the speed of light, one talks here of the future light cone and the past light cone of this event. Now, what about the events that are neither in the future light cone nor in the past light cone? They are neither in the future, in the causal future, nor in the causal past of our event, and they simply have no causal relation to our event. This is the key difference in causal structure. And when we now next consider Lorentz transformations, we require, as in the non-relativistic case, we require that space-time structure, and in particular causal structure, is preserved. Only that what's now preserved are these light cones, rather than simultaneity and duration.